Everyone, thank you for attending another Priberam machine learning seminar. Today we have Thomas Rolland. He's a postdoc researcher at INESC-ID, and he's going to give a talk on rethinking that in speech encoders. And you'll have time for questions at the end. So thank you, Thomas.
Well, first of all, thank you for inviting me, and very happy to talk a bit about my work. And yeah, let's just dive into it, right? So I'm not surprising anybody when I say that nowadays we're in this kind of era where we try to scale every machine learning model. And obviously this doesn't really escape with the speech encoder. So before explaining what is speech encoder, I'll just give you a couple of examples. So I tried for this presentation to like kind of gather information because there is none. You have for decoder only, you have NicePlot, but not really for speech. So I try to here show like a couple of models that are widely used in speech, but only the speech encoder. Oopsie. Okay, hopefully that's good. So yeah, you can see like I put here the parameter in billion, and we have like relatively small, but still very big, like 160 million. And then we can with Canary, which is from NVIDIA. And then we can go like, for instance, very famous one, which is Whisper, that's from OpenAI. And it's already very like a bit more than a billion. And then you have like models that are actually way bigger, like close to a billion. And like 3 weeks ago, Cohere released Cohere Transcribe that is mostly an encoder that do speech recognition, and is like almost 2 billion. So like you can see that, yeah, models are getting as well bigger. At least as encoder are getting bigger. So what's a speech encoder basically? So while in LLMs we have decoder only, in speech the speech is a bit more tricky to understand. So we usually need an encoder. So here I will mostly talk about 3 tasks. So we have speech recognition, where we try to convert speech, what I'm saying, into text. And we have like a speech encoder usually that encode the speech into a hidden representation. You can have the other way around. So you give text and you get speech as output. So this is TTS, where here the encoder is a bit different because obviously you need to do the opposite way. So this is what we call a text encoder. But later that you use the decoder and then the vocoder to generate the speech. But more recently, so there is the speech LMs. I think Ben 3 or 4 weeks ago in this talk actually talked about it. And what you can see is that on the right, basically, the audio is given to a speech encoders. Then if you follow Ben's presentation, you will see that you actually do some kind of operation discretization to basically get tokens. And the tokens are given then to the LLM. So this is speech LM. And as the speech encoder, speech task encoder are getting bigger and bigger, like they get really good. Like now we have really good speech recognition system. We're a really good CTS system. And the speech LM, even so it's early on, it's really good as well. But there is a catch. Obviously, it's not as easy. There is no free lunch, right? It's computationally expensive because it's getting bigger. So we have this 3 parameters. We have the train, the deploy, and adapt. So let's just get a bit more about it. So why is it a problem? Because the speech data is a bit complex to gather. So like usually over time, it's very easy to scale a model. You can play with hyperparameters and easily scale the number of parameters. But scaling data for speech is actually more tricky because, for instance, for speech recognition, you need to do the transcription. So this is an actual effort. And so over time, the data is not scaling as fast as the number of parameters in the model. And that's a problem because as we have more parameters, we need more like data to train. So we have the train problem. We have obviously, if it's getting bigger, we have the deploy problem because it's computationally expensive, especially on device. And then there is this adapt. Nowadays, we adapt model. So we take this pre-trained foundational model and we just fine-tune the model on our like smaller data set, for instance. Even that is risky because if you get a very, very big model and you fine-tune with a small amount of data, you have a higher risk of overfitting. So that's the free catch that basically I'll try to cover a bit today. But before jumping it, I want to give just a bit of a short introduction on what I've been doing on this last part, and then because it will give intuition on why we do something else later. So yeah, let's talk about the adapt. So I call it the parameter efficient fine-tuning, so the PEFT band-aid, because I call it band-aid because it's only solving one of these 3 aspects. So as a setup, my thesis was about children's speech recognition. So I'm gonna use a speech recognition task for children's speech. And I have roughly 100 hours of children from grade 3 to 5. And it's spontaneous speech. So they're just talking basically with a virtual tutor. Children's speech is really hard to model. So that's actually quite challenging task. So as a model, we use a regular transformer, but here we have a speech extension of the conformer, which is a conformer. Basically, the only thing that changes in the encoder, we have like 2 feed forward instead of 1, and we have a convolution basically after the multi-head, but that's it. And this has been pre-trained with adult speech already. So we have with this very commonly used data set in speech, which is a Libre speech, almost 1,000 hours. So you see already that the children data, we only have 100, and like adults, we already have 10 times more. So there is a data imbalance here. And obviously, the first thing you will do is fine-tuning, right? You take the entire model, you fine-tune on the children's speech. And when you do that, you get improvement. So this is word error rate. So the word error rate, the lower is the better. The best case scenario is 0%, which means you have perfect recognition, but it rarely happens in real life. But yeah, like so fine-tuning is working. That's pretty cool, but we use the entire number of parameters, and that's a bit problematic. So during my thesis, the idea was like, how far can we push this parameter efficiency while preserving the performance close to this full fine-tuning? So we did a first experiment that was called partial fine-tuning. So on the left, it's more or less regular. What we did is like we fine-tune just layers. For instance, either the layers at the input of the encoders or the layers at the output of the encoders. And what we saw is like in our case, the layers at the output of the encoder were more important to fine-tune. But this is roughly like people are using it for a while. What we proposed there was to, instead of fine-tuning layers, what if we fine-tune components? So maybe like for children, we just need to fine-tune the attention. Maybe we just need to fine-tune the FFN. And so we did here on the right. And what we saw is basically fine-tuning the feed-forward component in this transformer architecture is actually what were giving us the best results. And that's already better because we go from 100 to like 60 million parameters. So it's a bit reduction, but not much. While getting better performance and full model fine-tuning. But when you think about parameter efficient fine-tuning, you often think about LoRa and adapters. So we obviously try that. At the time when we tried it, LoRa wasn't even existing. So I don't have experiment with LoRa. I'm mostly gonna talk about residual adapter. Basically, the idea is that you take your pre-trained model, you keep it frozen, and you plug this extra set of parameters. And during training, you just fine-tune this extra set of parameters. And this is basically just 2 linear and a really in the middle with a norm at the beginning. So we did that. It was really unclear if it was going to work with children's speech because children's speech is very variable. So we were not even sure it was going to work. So we evaluate that. We also evaluate where to plug them. And what we saw is that it actually makes sense to plug them in parallel of the feed forward, which is in line with what we saw before. Like since the best thing to fine tune is the feed forward, it somehow makes sense that where you plug these adapters is like on the feed forward. So here this is just for the regular transformer, and this is for the conformer. As you have feed forward, you have 2 adapters basically. And doing that, we can see here, I changed a bit the plot, but basically the idea is like you have the number of parameters here, and you have here the performances. So the best case scenario is to be in this kind of bottom left corner. And you can see that the full fine-tuning is really not is good, but it's not parameter efficient. Then the partial fine-tuning was a bit more parameter efficient and better than full model fine-tuning. And the adapter is even more parameter efficient and still beats as well the full model fine-tuning. But we were really curious, what about if we zoom in this kind of circle? What happened if we try to get even more parameter efficient? And turned out that during when we did this study, there was like a couple of other parameter efficient models that were available. So we decided to try them. So we try, like for instance, different version of the adapters. We try one where we like instead of having a linear, we try convolution, either up or down. We try the even more parameter efficient one. And what we can see is that this one is actually quite good. So it's half basically compared to the initial one. So that's nice, right? We get even more parameter efficient while still beating the full model functioning. But then when we try to be even more parameter efficient, we see like there is a degradation, like the performance will be increased, and that's not something we want. because what we want is we want to be here, like in this yellow region. And that's all of this kind of introduction. The idea is like to basically present this because it's going to be important for the rest of the presentation. So basically, what we saw is that this FFN where we plug basically our adapters since the beginning are really redundant in between layers. And this has been showed for LLMs and for decoders only. And it has been more or less shown as well for speech, but for speech model, but it wasn't fully sure at the time. So if the FFN are redundant in between each other, instead of having one adapter per feed-forward per layer, we're wondering what happens if I have one adapter that is shared across all the layers. So basically weight sharing of the adapters. So we have the regular one where we share basically one per FFN, but like no matter the layer. And then since we have 2 feed-forward, we can even go crazy. What about having a single one that is shared? So a single adapter. And the nice thing about that is that since you share by the number of layers, the parameter reduction is the number of layers that you have. So we had 12 layers, so we divide by 12 the number of parameters. So that's why we go from 12 to like 1 million. And if we plot that in the...
Can you clarify one of the direction of the arrows?
like this one?
This is correct, but on the other one?
Yeah. So this, like basically it's... this one.
There's one arrow that has no direction there. So
yeah, that's actually here. Yeah. So basically what it does is like this, then this, and then this and this. Yeah, so basically it's the same as this, but just imagine that this one and this one are like the same. Like they share the same weight. Yeah. Could have maybe make it a bit more. Is it more clear?
Yeah, I understand.
Yeah. And yeah, so like if we actually train that, we can see that now we have like this, our models here that is actually in the region where we're targeting. So that's pretty cool. And let's show that, yeah, there is like, it looks like there is some redundancy as well in speech in this FFN. So that's nice. We show that parameter efficient can solve the adaptation problem. That's pretty cool, but we still have the base model that is really big. And that's still the problem for like both the training and the deployment, as I mentioned before. And it's nice, but yeah, we need to remove this band-aid, basically. Like we need to try to solve this too as well. And the question we're wondering is like, why are the base model, this base model are so big in the first place? Maybe we can reduce them. So yeah, like now we're gonna focus on that. So to understand why they're so big and why like is there redundancy and stuff like that, we decided to look inside the black box of these speech encoders. And it turned out that we didn't have to do it. Some people did it before us. Last year, actually, at ICASP, and they analyze basically what happened depending on the layers. So they take encoders and they take they give an input to the encoders, and then they compare the output of every single layers compared to all the other layers. And then they do some kind of similarity measurement on the right. And they did that for a couple of models. And what we can see is that there is a region like here, and like here, where basically the layers are extremely redundant. The outputs are extremely redundant, which means that there is over-parameterization. And it also means that in these kind of layers where they're really redundant, they just pass through the information and they just do some kind of repetitive refinement over the signal, right? But this is like Web, PUVEC, WebLM. And the one I'm more curious about was to use like the Whisper, so the one I mentioned at the beginning from OpenAI. So I just replicate this experiment just for the fun of it, basically. And I did it with two sizes of Whisper, so the Whisper medium and the Whisper large. And basically we observed the same thing. So that's pretty cool. Basically the observation was we confirm it. And yet I was not fully satisfied by this plot, because every single time you give a single input and you get the output at every single layers, but like you always change the input. So like if you compare the first and the last, they will be very different because they will go through all of this operation, all of these layers. So what I decided to do is do another plot. So this one, where instead of giving one random or one input and then get the output at every single layers, at every single layers, I will give the exact same input and I will compare the output of every single layer, basically output. So basically I will see how different the operation of this layer is compared to the other one. And here we can see it's a bit different, but yet very cool. Basically, we can see that the first layer, so layer 0, and the last layer, the layer 23 in that case, they're really different from the other operations. So somehow the first layer is doing some kind of projection, and the last layer is for the ident representation. And the last layer is also doing some kind of projection, which is what the decoder is expecting, the dimension that the decoder is expecting. And in the middle, we see that we don't change that much the operation. So there is a high redundancy here in this middle part. So that's pretty cool observation. Let's use it, right? Let's exploit this redundancy to maybe do some kind of more efficient model. To do that, you have different methods in the literature. You have like quantization, knowledge distillation, pruning, lowering factorization, and weight sharing. But we noticed that all of this one require a trained model, and that's not what we want. We want to train a model that is small in the first place from scratch. So that's why we decided to focus on the weight sharing. Also because the shared adapter were working, so we were thinking, okay, let's just keep going with this experiment, basically. And the idea is like, since we have weight sharing, we can do this repetitive refinement. And we were thinking, okay, maybe we can exploit this. But so which components need to be shared? Like which one is actually doing this repetitive refinement? So that was an analysis we need to do like in the first place. So to do that, we have more or less the same setup. The only thing that differs is this time we're also going to train the pre-trained model. So we're going to train with the adults, so the Libre speech dataset, the 1,000 hours. And then again, since we're going to have a smaller model, we still wanted to be sure that it doesn't lose this ability of doing fine-tuning. So we're going to keep doing the fine-tuning on children. And for the rest, it's the same model, like 12 layers and for the encoders and 6 layers for decoder. In terms of configuration, we tried a couple of configurations. So the original one, where we don't share anything, basically, like, which is basically our baseline. So the equivalent of the twin of the shared adapter, which is the shared FFN, where basically we have a single FFN, like no matter the layer, and like then we have another one. Here there are two different. This is not the light version, but still it's good reduction. Then we do the share multi-head attention. We also did the same with the convolution, but I don't have space to put here. And then we try this version here, where basically instead of sharing components, we're gonna share layer. So basically, as you know, you can have a single layer, and like you get input, you go through the layer, and then the output of this layer is sent through again. Basically, it's a kind of recursive. So we call it the shared transformer and the shared conformer here, and we do that like 12 times. Okay, so let's just look at the result. So pretty nice. So we have the non-sharing, which is our baseline. We have the transformer and the conformer here. And if we only share the multi-head attention, we can see that there is a degradation here. So here, I forgot to mention, but this is water and clean. So this is easier kind of audio. And then you have the other, which is a bit more challenging audio. And what we can see, sharing the multi-head attention actually degrade here. So it's not big degradation, but still a degradation. But sharing the FFM is actually not degrading that much, which was more or less what we expect with the shared adapters experiment. So that was really nice. But when we look at the conformer, we see that the shared multi-head attention is actually not degrading that much compared to like what it was here. And we hypothesize that basically the multi-head attention, it works like a feature extractor, and the convolution in the conformer also works as a feature extractor, so they somehow compensate each other. But overall, like sharing is actually very close to the baseline, and we get like quite good reduction. Like we can get 60% reduction, for instance, and we don't lose that much in terms of performances. But what's really interesting for us was these two results here. If we share a single layer and we loop 12 times over it, like we get a parameter reduction of the encoder of 93, which is like huge reduction. And yet we don't get that much of a degradation compared to the baseline. So we're really curious about that. And one thing as well is that when we fine-tune, we see that the fine-tuning ability, even on the small model, is not lost, which is something that is pretty cool for us. So these two lanes, so the shared transformer and shared conformer, actually has a name in the literature. It's called recursive transformer or loop transformer. There is a lot of name because it's really growing field. So I'll call it recursive transformer for the rest of the presentation. At the time when we did that, so it was 2024, nobody come up with a real name. So that's why we call it the shared initially. But if I have to redo this paper nowadays, I'll most likely call it recursive, I think. So yeah, let's talk about this recursive transformer, right? As I say, it's been like investigating right now. Like this gain a lot of attention since the last year, more or less, even more nowadays, because like there is a speculation on the internet right now that's the latest model of anthropic, the Mythos model that they don't release. Some people, it's just speculation, we don't know yet. They say that it might be a loop transformer. I will believe it when I say it. But yeah, so like it's really trendy somehow. And the nice thing about it is like parameter efficient, right? As I mentioned, this is what we did it. But people found that this kind of, for LLM, they found that basically it's very nice for scaling test time compute because they allow to do some kind of chain of thought within the latent space directly. So you don't have to go through like the text space again. So you can directly do this latent space reasoning inside of the model directly. And that's more or less what we can see here. I just show that basically it's for harder tasks, like more that require more reasoning. They found here on the stop right experiment, they found that basically it's better to loop to not looping. That's where reasoning is actually nice. One other thing that is cool with this is that since you can scale now the depth, because you can loop as many times as you want in a way. So you can scale this virtually the number of layers that you have in terms of depth. So you can improve the knowledge manipulation. And nothing like stop you as well to decide when to stop. So you can say, okay, I don't want to loop anymore. So you can have an adaptative computation saying like, I would just want to do one loop or I want to do 20 loops. And yeah, so it's pretty cool, but this is decoder only, and this is LLMs. And I'm working with speech and I'm working with encoders, and it's unclear if this will extend to speech encoder, right? We have, obviously, since everything I showed you before, we have initial idea that it will, but what it will be cool, for speech, it will be cool because as we showed earlier, we have this iterative refinement happening already within this model. So it will be a natural fit for speech, but also like we didn't investigate it, but it's also cool, this dynamic number of loop, because if you think about it, if you think an audio signal will be like, well, a part of an audio will be very easy to like for speech recognition, the silence, you don't need to do anything. So this will be very easy to actually interpret. But then if you have a phoneme transition, for instance, that would be very hard. So these two might not need the same amount of computation. Like I guess the silence don't need to do as many like computation because it's really easy. While the other one might need more loops. So this is why the dynamic number of depth could be used for harder frames, basically. But as I say, we didn't investigate that because one thing at a time, right? So first we need to understand how are they working and why. So basically we have this question in mind. So how many layers can we share? Can we like, what do we need to share actually? Because so far in the previous experiment, we just had one layer and we just share one layer, but maybe there is a better way, especially if we see like, for instance, that we have parts that are really different from each other. So maybe we need to like decouple these two. So do we need to keep non-shared layers as well? So basically this first two questions is like about what's the configuration we should use. And one thing that was also very cool and very interesting for us is like, how many loops basically? What's the amount of loops? How does he influence on the results? What's happening with the looping basically in speech encoders? As I said, for the configuration, we have like this first layer that is very different. So this is a blue area, right? We have this middle part that is really most likely shareable. This is our yellow part. And then we have the lightest, it's green, not really on the projector, but it's super green, right? And that is also the last layer that should be also different. So if you keep these three blocks, maybe we can have some kind of configuration that looks like this. A solid blocks where we have basically non-shared layers, a recurrent block where we actually have our recurrent layer, so we can share many layers and we just loop over it. And then some coda blocks basically that are like non-shared as well. So basically we try to have, as I showed before, like these three different blocks configuration. Now we decide to go with a slightly bigger model with a 24 layers encoders, 24 layers decoder. It's basically in line with the Whisper, so this one that we have on the right. But again, we train it from scratch, again with the same amount of data, which is the adult 1,000 hours. And yeah, so let's take a look at the result, right? So all of these are using the same amount of flops, so you will see the same amount of layer virtually. But just to see basically how this will influence, the configuration will change. So NR is a number of elements that you have in this yellow block. The L is a number of time you will go through this yellow blocks, the recurrent. So one means you will only see with one time, which is basically no looping, right? And NP&C is basically the number of layer in the non-share at the beginning and non-share at the end. So that's basically what we have here in this configuration. So the baseline is this one. So this is our baseline. Then we have, if you compare to what we had before, so one layer is looped this 24 times. In this case, that would be R4. So that's where we get the 95% reduction. Then we play in the middle, trying to change a bit. So like, what if we had more layers and less loop? What if we had more layers? If we had less layers, but then more loop? And what we see is that there is some kind of degradation, right? Which makes sense. You lose layer within this shared block. So it makes sense. But at the same time, you get a small degradation, but you get way more parameter efficient. So there is a trade-off here. But then we, as I mentioned, maybe the blue and the green blocks need to have some element in it. So that's what we did in this L that stands for latent. So latent 1 and latent 2, where we basically take this, that was this one and this one, and we tried to, actually, there was, this one and this one. And we try to basically add 2 at the beginning and 2 at the end. And what we can see is like this basically are better. Like doing this latent non-sharing at the beginning at the end is actually the best configuration. So this is obviously a work I was doing with Carlos that is here and Alberto that is here as well. And Alberto got a crazy idea. He's like, what about we take the baseline and we just loop over the baseline? So we don't really care about the parameter efficiency anymore. What would happen if we just loop, basically? And that's what we did in this L3. So here you see that in terms of parameter efficient, we exactly the same as the original of the baseline. We just loop 5 times, basically, and we keep 2 at the beginning and 2 at the end. And what we can see is that even so it's way worse in inference, right? It gets better results. And this is pretty hard. Libre speech is pretty hard to get better results. So that was pretty interesting results. So that's about the configuration. Then we try, obviously, since it's a full work, we decide to be sure that it's not just because we train Libre speech, so this English American, and on this transformer architecture. So we just try on Mandarin with a transformer. And we saw that basically the same thing is happening. We see a small degradation, but not much. And we also wanted to try so another. We showed the transformer is working. We showed the conformer is working. And there is a third kind of in a family of models that is called the branchformer. So we just wanted to be sure that the branchformer is working. And we see that the branchformer is actually working very well as well. So basically, it's working no matter the language, no matter the model, which was pretty interesting. Okay, but what about the looping, right? So that's a looping experiment. So we take the latent, so the latent 1, which is this one, which was our best trade-off, what we consider to be our best trade-off, and we're gonna play with the number of loops from this one. So here, basically, this will be faster inference, and this will be way worse in terms of inference. So the number of flops here differ. And what we can see is that basically no looping is the worst that we have. So no looping is not a good scenario. And then starting adding loops, we get better results. And then around 10 to 20, that's where we degrade again. So there is some kind of trade-off to find. But we were curious about what aspect is getting better with this looping. Is it because the audio is more tough? Is it because the audio is longer? Is it because there is more words? So that's what we have on the right. So this lane here is basically the performance of the non-looping. And then we compare each time for these different scenarios. So here, for instance, for all the utterance in the test that are shorter than 5 seconds, all the utterance in the test are longer than 20. And we see basically all the looping is behaving compared to non-looping, just to see what's happening. Duration-wise, not much, right? It gets better, but we don't really see a trend happening, no matter on the duration. We tried word count. It's close to the duration, but not always. It gets better for very short utterances, especially for using 2 loops and 5 loops. But what was really interesting was the word error rate. So basically what we say is we take the word error rate the word error rate as a criteria. So basically here means very, very easy utterances to recognize, it's already very good using the 1 loop. But then if you go here, this is really tough utterance to recognize. Above 20% word error rate, which means it's really hard utterance to recognize. So it's really complex data to interpret. And what we see is that if it's easy data, the looping doesn't provide anything. But then if you add the toughest data and you add looping, that's where you actually benefit. So it's a bit in line with what people have been seeing with the decoder in the LLM. It's basically some kind of reasoning ability, right? It's more complex and you get better with the looping. So we tried two things as well. That's the last thing I promised. I think I'm always a bit fast, but anyway. We tried two different way of training the model as well. The first one is basically we try to use the duration criteria, because at the time we didn't do this experiment. We tried to use the duration criteria to like decide the number of loop. So if the audio is very short, it will be like one loop. But if the audio is long, it's gonna be 20 loops. It's getting like okay result, is more or less in line with what we had, but that makes sense because the duration is not a good criteria. Now actually doing the same thing, but using the water rate criteria, because that we believe is gonna be better. But what's interesting is the second line here. So basically what we do here is we start with a model that is no looping. And then during training, we add more loops during the training every like, I don't know, like, I think it's every like one or two iterances with one or two epoch, we just add more loops. And over time, and at the end, we'll have 20 loops. And during inference, it will be 20 loops. So basically, we're converting a model that is non-looped to a model that is looped with a large amount of loops. And what we can see is that this one is actually really good results. And like compared to the 20 that we had here, that is really good. So basically, it looks like we can convert this non-looped model into a loop model very easily, basically. And yeah, that's it. Pretty in advance, I think. So yeah, in terms of conclusion, so we went from this heft, so the parameter efficient for large model. Then we observed that there was redundancy, and we start using it to do this recursive weight sharing. We find that, yeah, it's a good way of doing efficient because you can always stop the looping before. So that could be nice for efficient machine learning. And that's something I think it's interesting because we move beyond this brute force where we just scale and scale. Now it's another way of scaling without exploding the number of parameters. And what we're trying to do is right now is we're trying to convert pre-trained model that are non-looping into looping one because we saw that it's possible. We also would like to investigate on early stopping strategies, maybe like, as I say, like silent frame would don't need as much maybe looping than the complex phonetic frame. So that's early stopping strategy. And as yet, because we're sharing, we're gonna lose a bit of degree of freedom, right, in the expressiveness of the layers. So maybe adding some kind of low rank adaptation will help to recover basically this performance that are lost. And yeah, I think that's it. So if you have questions, I'm more than happy to reply. Yes.
I do have a question. Is it mine?
Yeah.
But people will know. Understand the response. So very nice talk. Thank you.
Thank you.
So in the previous slides where you talked about adaptation, so could you have you thought of right last bullet from the start?
This one, yeah.
So I had a question before, but you mentioned it, yeah, the closest reference. So the adaptation does not have to be shared, right?
Yeah, exactly, because there is less parameters, so you don't.
Something which is halfway between a fully shared model and partially shared.
Exactly, yeah. Like
should easily tell more the type thing because it's additive.
exactly. So that's the easy way. Like obviously nothing stops you as well for doing some kind of mixture of LoRa where you have like multiple and you can even maybe share it. Like that's one thing that could be tried as well.
So the other thing that you mentioned as a possibility that you had not thought yet.
Yeah, the dynamic. Yes.
Do you have any idea how to?
Yeah. There is a lot of work going on, especially on the microphone. There is a lot of work going on this particular field, but for decoders, there is one that is really getting a lot of attention last summer, which is mixture of recursion, where they have a router basically at the beginning of the loop, and they decide with the router how many loops you will need. They do it either at the frame level or at the utterance or the full utterance level. Like there is also like an easy way, which is you just compare the output of the previous loop compared to this loop, and you see if you don't change anymore, that means that you most likely find a good point and you can already exit because you won't change that much. So there is a lot of strategies. I think the mixture of recursion is the most interesting one, and it's the one that brings so far the best result.
And you also learn
You learn as well the router, that decide how many loops you need to do.
Is anyone else?
I technically talked. I just have one question. Could you explain again the slide before that one, the part about the adaptation and
This one?
yeah.
Yeah. So like the idea was like at the beginning of the training, we train the model normally, like no looping whatsoever. And then after a certain amount of training time, so a certain amount of step, we decide, okay, now instead of having one, so passing through this recurrent block one time, we're gonna pass it twice, basically. We just start looping and we start with two. And obviously you will have a spike because the model will be lost at the beginning, but then you will easily recover from it. And then when you more or less recover, we decide, okay, now what about 3 loops? And we basically do this during the entire training. And by the end, we do 20 loops. Is it more clear? And first time, it's always 20.
Let me see, understand. So you are training from scratch.
Yeah.
And but why not add all the loops at the beginning of the training?
Because that's what we did here, right? This is what we do here. We do the 20 loops right at the beginning and we see a degradation. So we're thinking maybe that's just too much, to digest for the model in just like one time. So instead of giving him, okay, you need to do 20 loops right at the beginning, we say just start easy, start with one, and then like you do like 2, and then you go until the 20s. And yeah, basically we tried since the beginning, but yeah, it wasn't as good.
Thank you very much.
No question?
I just want to check something because at some point you said that the various configurations share the same FOPs.
Yes.
I think wasn't this one, was it?
In this one, yes.
Right. So
because virtually they see the same amount of layers. They see 24 layers every single time.
sorry, what?
Because like physically you only have like less layers, right? That's why you have the parameter efficient. But that virtually you will see the same amount of layers. You will always see 24 layers. So the same amount of operation will be done basically compared to the original one.
I don't think I understand what you said.
Oh, okay. Yeah. So basically, since the goal here is to get parameter efficient, but I wanted to compare.
Yeah, sorry.
Okay, yeah.
Yeah.
Yeah. So basically, if you do the math here, you're always gonna find out 24 here. Yeah.
Yes.
Not well. Even on this one, not on the last one, the fun one. This one is different. This one you will have like 20 times 5 plus like 4.
Yeah.
So that's why you get way more basically.
It's a very expensive.
Yeah, it was more like for the fun of it. We decided because we're sure a reviewer too were going to complain about that, so we were thinking we do it, so he won't complain about it.
Yeah. So it's a little about this idea of like having the same flops, etc. If you go back to the last slide, I was actually wondering, yeah, the one we did say, well, this is unfortunately.
This one?
Yeah, this one. So about this idea of like increasing the number of loops during training.
Yeah.
This would also lead to like the final training that we do from like 0 loops to 20 loops.
Yeah.
It's also like a much longer training.
Yeah, it is.
So the model is technically also seeing a lot more
Yeah.
data as well.
Yeah.
Okay.
It's still faster than this one, obviously, because you start with.
Faster.
It is because this one sees 20 loops all the time, so it will be always longer, right?
Okay.
Yeah.
Okay. I thought you would do like the full training on 1 loop and then 2 loops and then 3 loops, etc.
Yeah. But so basically, when you have 1 loop, that's faster because you have less
Yeah,
operation.
exactly.
Yeah. So the beginning is faster. Yeah.
Comparing those two settings, do you have the same amount of weights that you learn on the model?
Yeah, because like physically you have the same amount of layers. In all of them here, you have the same physical number of weight that is the same. So that's why I don't put here the number of parameters because it's always the same here. The only thing that changes is the virtual number of layers that you're gonna see. Basically.
That's very. That's a weird thing.
It is, right?
Yeah.
Like it's. But it's really like we were really surprised, to be honest, when we did this basically like this experiment here. That's why I put it in red. Like really surprised when we get this result. That was like I wasn't expecting that, to be honest. But yeah, I mean it is like, and we showed it is. So yeah,
Do you have the percentage of the training epochs that you do on each layer?
Sorry.
The percentage of the training epochs that you do on each layer. So since you always train the first layer one time for each epoch,
Yeah.
and the last one also one time.
Yeah.
In the middle one, what happens? You train for a lot more.
You mean in terms of backpropagation? So we tried two things. I didn't mention it here. We tried two things. The first one is just to keep it like that and just let PyTorch deal with itself and backpropagate through all the entire iteration, so the end time. And it works. That's the result that we have here. That's the result that we have here. It works very well. But I was also curious because I saw a paper. I think it was the second one. In the second one, they do a slightly different thing where when they backpropagate, they don't backpropagate through the entire looping. They just backpropagate through the last iteration. So I tried that as well, but it gets slightly worse results. So it's better for training because you use less GPU, right? But performance-wise, it's not as good. So yeah. Yeah.
In the last slide,
The conclusion one?
yeah, on that last
Yeah.
point of the whole record adaptation, does that remove the possibility of doing as many loops as you want?
Yes, that's why I'm happy with it. That's why I was mentioning maybe a shared mixture of LoRa will make sense. Or there is a lot of work that can be done here. There is a work that I read not too long ago where basically they use an hyper network to actually learn the LoRa weight. So you could maybe use that as well. There is basically a lot of things to be done here. But yeah, you lose the dynamic aspect. You could always though decide, okay, this is gonna be my max number of loops. You can say 20 number of loops. And then you know that's what's the maximum number of LoRa that you need. But that's the only way if you want to add as many loop and you don't have this maximum, yeah, then you have a problem. Yes.
So you showed that the importance of recursion is highly dependent on the difficulty of the sample.
Yeah.
Have you thought of implementing something where you can determine dynamically how difficult a sample is and then determine the number of recursions you'll need based on that?
Yes, so I thought about it. I didn't do it yet. But yeah, like that would be one thing to do, right? Is to decide beforehand, like, okay, this sounds like an easy or a tough utterance. What about like I do more loops? Yeah. So far I haven't done it. I'm trying to do it in just to proof of concept. So right now what I'm doing is I'm replicating this experiment basically, but with warrior rate. And if it works, then we can move to the dynamic one somehow. Yeah. But yeah, I thought about it. Yes. Thank you, everyone.